is the last of Unit 15, the last piece of information that we're going to cover in our reaction rates, and it is the Le Chatelier principle. I am probably not pronouncing that correctly, but that's the best I can do. So you may hear it said differently, but all means the same thing. And Le Chatelier deals with reactions that are in dynamic equilibrium and what happens to them if you stress them. So first of all, this whole dynamic equilibrium thing. So dynamic equilibrium, remember, dynamic means that it is changing, but the equilibrium means that it is staying the same. So the dynamic part is true. The reaction is occurring. It is a reversible reaction, which means you have this double-headed arrow that you are dealing with. The equilibrium part means that visually it is remaining the same. And so it doesn't look like it is changing, but there is a continuous reaction going on. Now, if it is dynamic, the change is happening. If it is an equilibrium, it looks the same. But what happens if you change something? And there are three ways that you can change the system, or three ways that you can stress the system. One is by changing the concentration of either the reactants or the products. Another is changing the temperature, either cooling it down or heating it up even more. And then the third is the pressure, adding or taking away pressure. So we've already talked about these four things in terms of how they affect the number of collisions, how they affect just the rate of the reaction. And so now we're going to talk about how they act as a stress. The one thing that we've already talked about in this kind of list that we will not deal with Le Chatelier is catalysts. Catalysts have no effect on equilibrium. They only affect the activation energy. So equilibrium is going to be achieved whether there is a catalyst or not, but it will not do anything to unbalance or to stress the system. Okay, so our first stress on our system is changing the concentration. And there are four ways to change the concentration. You can add or subtract some of the reactants, or you can add or subtract some of the products. And so these four ways will change the equilibrium. They won't be the same anymore, and so that equilibrium is thrown off. And so it will have to, in order to get back to equilibrium, adjust. And so I like to kind of think of it when it's at equilibrium like a balanced seesaw. And so you have everything level, everything on either side, has the same weight, or however you want to think about it, but it's nice and level. And so what if I do something to change either side? And so our very simple example equation is A plus B produces C plus D. It is a reversible reaction, so you have our double-headed arrow. And right now, everything's in equilibrium. Everything is balanced. It is a forward and a reverse reaction that are taking place at the same rate. But I mess it up somehow, and I come along and I add more. I add more reactant. So I add some more A to the reactant side. So now all of a sudden my seesaw, instead of being level, is heavier on this side. So now it's kind of tilted this way. So the reaction is not in equilibrium anymore. It's stressed out, and it will adjust. And in Le Chatelier speak, you would say that one side or the other is favored in this situation. In order to get it back to level, in order to get that purple line that I have there, the tilt, back to level, I can do one of two things. Now, I've already messed with the reactant side, so now I have to adjust on the product side. And so in order to get back to equilibrium, the reaction will shift to produce more products. So a lot of times they will basically say it becomes a forward reaction, or the products are favored. It will just go forward until you have an equaling out of the products and the reactants until it makes up for that extra A by adding to the C and the D. And so it will be a forward reaction until that point is reached, and then you get back to equilibrium. Okay, so now I can change it also by removing some things. So say that I now decide to remove some of the reactants. So if I come along and I remove some of this B, now all of a sudden my seesaw goes the other way. Now the A and B, with the B being gone now, are lighter. And so my seesaw tilts the other way, and the reactant is not in equilibrium anymore. So right now it is stressed out, and so the reaction wants to get back to normal. And in order to do this, it needs to get heavier on the reactant side, and so it will shift to produce more reactants. And so for a little bit it becomes a reverse reaction, and you see the reactants being favored. And so until it builds up enough of the B again, of the A and B, it will be stressed out. And once it gets the B concentration, the B amount built back up by the reverse reaction, then it will get back to equilibrium and everything will go back to normal. Now, same thing with changing the products. So if I added more products, I would be adding to that side, so you would become unbalanced, and our reaction would shift to produce more reactants. Okay, and so the reactants would be favored in that situation. So it's just like this reaction that we said before. So A plus B, here's our double-headed arrow, is C plus D. So if I'm adding to this side, A plus, or more D over here. So I'm heavy over here, so it's going to shift away from that to produce more of the reactants. And then same thing, if I remove some of the products. So now all of a sudden I have fewer products, it's lighter on the product side. So the products will be favored and it will shift to produce more products. So there's no math involved in any of these steps really, but there can be math, so just kind of be aware of that. Remember, we're doing kind of the basic intro to all of this. But this is the first way that Le Chatelier will affect a system, and it's changes in concentration. Okay, so now this next change that we could have, or this next stress that we could apply to a system, is changing the temperature. And so we've talked quite a bit about temperature, and you know that temperature-wise you either have exothermic reactions or endothermic reactions. And if we're talking about exothermic reactions, we know that that is when heat is being released. Heat basically is a product in an exothermic reaction. And then if you are having heat being absorbed, it is an endothermic reaction. Heat is having to go into the system. So again, if you're color coding yours, here endothermic heat is a reactant and exothermic heat is a product. Okay, so you would have to know, basically, am I dealing with exothermic or endothermic reactions, because that tells you where the heat is. And if you are stressing that system by changing the heat, if you are increasing the heat, then it will cause a reaction to shift to absorb the heat. So basically it will move away from where the heat is. If you're decreasing the heat or the temperature, then the reaction will produce more heat. And it doesn't matter which side it is on, it's still going to either go away or towards it. So here's our example. And it wants to know what type of reaction is this. So I have heat over here as a product. So first of all, that means that this is an exothermic reaction. So the type of reaction. And then our second question, what happens when the temperature is lowered? What happens if I basically, just like we did with the concentration, if I take away the heat, if I lower the heat? It's basically like me saying I have taken away one of the products. And so to get back to equilibrium, if we're still dealing with heat or change in temperature as a stress, to get back to equilibrium, this reaction will shift to produce more product because heat is one of those products. So what happens when temperature is lowered or taken away? It will, and you can say it in our Le Chatelier lingo, it will favor the products. Okay, so now if heat had been one of the reactants and I had lowered the temperature, it would have favored the reactants to build that heat back up. Okay, so now change in pressure. This is only going to It's only going to apply to systems where all of your components are gases. And so when you increase the pressure on a gas system, it will shift towards the side, or it will favor the side of the reaction where you have the lower number of gas particles. So this one is pretty straightforward. So what you would want to do in our example is you would want to look and see where do you have more gas particles. And this is basically just adding up the coefficients for all of the gases. So for this side, I have 3, and then remember there's a 1 here. It's an understood 1. So I have 4 gas particles versus 2 gas particles. And so I'm going to work it kind of like we did the concentration. That means that all the pressure is over here. Okay, so that's where the pressure is. So if I am going to increase the pressure, so I'm basically putting more pressure over here, just like we did with the concentration, then it will shift away from that because now it is unbalanced. There's too many reactants. And so it will shift towards the products, and products will be favored. Same thing if I came along and I took away some of this pressure. So here is my original equation again. If we're back to the original reaction with my pressure on this side because it has 4 gas particles versus the 2. If I am decreasing the pressure, I'm taking that pressure away. And so in that case, it would shift towards the reactants in order to build back up to our original or to our equilibrium conditions. Okay, yay, we are finally done with the notes for Unit 15. Let me know if you guys have questions over Le Chatelier. I will be sending you some questions to work on these and some problems to go through for this tomorrow. Thanks, guys.